Now we will show some previous attempts to change standard units for some rotational quantities, and explain why they failed. Attempts to establish new standard units for rotational quantities has been done through dimensional analysis of plane angle. Plane angle may be defined as theta equals s divided by r, where theta is the magnitude in radian of the subtended angle, s is circular arc length, r is radius of rotation. 1 radian corresponds to the angle of which s equals r, hence 1 radian equals 1 meter per meter, which is equal to 1. However, radian is only to be used to express angles, not ratios of lengths in general. Giacomo Pronto writes, the current state of affairs leads inevitably to ghostly appearances and disappearances of the radian in the dimensional analysis of physical equations. For example, an object hanging by a string from a pulley will rise or drop by y equals r times theta centimeters, where r is the magnitude of the radius of the pulley in centimeters and theta is the magnitude of the angle through which the pulley turns in radians. Radians appear on the right-hand side of the equation but not on its left-hand side. Similarly, in the formula for the angular velocity of a rolling wheel, omega equals v divided by r, radians appear in the units of angular velocity but not on the right-hand side. Anthony French calls this phenomenon a perennial problem in the teaching of mechanics. Oberhofer says that the typical advice of ignoring radians during dimensional analysis and adding or removing radians in units according to convention and contextual knowledge is pedagogically unsatisfying. At least a dozen scientists between 1936 and 2022 have made proposals to treat the radian as a base unit of measurement for a base quantity, and dimension, of plane angle. Quincy's review of proposals outlines two classes of proposal. The first option changes the unit of a radius to meters per radian, but this is incompatible with dimensional analysis for the area of a circle, pi times r squared. The other option is to introduce a dimensional constant. According to Quincy, this approach is logically rigorous compared to SI but requires the modification of many familiar mathematical and physical equations. A dimensional constant for angle is rather strange, and the difficulty of modifying equations to add the dimensional constant is likely to preclude widespread use. Let's list down all pros and cons of each option for standard units of rotational quantities, so we can easily understand what's at stake here. Option 0, keep using current standard units. Pros. Nothing needs to be done. Just continue business as usual. Currently existing textbooks can still be used. Requires less characters because some unit of angle can be omitted. Cons. It leads inevitably to ghostly appearances and disappearances of the radian in the dimensional analysis of physical equations. A perennial problem in the teaching of mechanics, where radian appears on one side of an equation, but not on the other side. The typical advice of ignoring radians during dimensional analysis and adding or removing radians in units according to convention and contextual knowledge is pedagogically unsatisfying. Inflexibility of conversion between radian and other units of angle in some equations, which will be explained further later. Option 1. Change the unit of a radius to meters per radian. Pros. Solve the problem from option 0. Rotational quantities can be expressed in consistent units with each other. Cons. Incompatible with dimensional analysis for the area of a circle, pi times r squared, or volume of a sphere, pi times r cubed. Option 2. Introduce a dimensional constant. Pros. According to Quincy, this approach is logically rigorous compared to SI. Cons. Requires the modification of many familiar mathematical and physical equations. It is rather strange, and the difficulty of modifying equations to add the dimensional constant is likely to preclude widespread use. Option 3. Change the unit of a rotational radius to meters per radian, while keeping the unit of a geometric radius in meters. A radius is geometric if it can still have a defined value while the object is stationary. Rotational radius is only defined when there's a rotation. Pros. Solve the problem from option 0. Solve the problem from option 1. Cons. Something needs to be done. Currently existing textbooks need to be revised. Requires more characters because the unit of rotational angle cannot be omitted. People need to unlearn the old standard and relearn the new standard, which can be hard for some of them. Note, all options except option 0 share these cons. Now let's consider if the benefits offered by the last option worth the efforts to change the current standard. This is an article titled The Radian, That Troublesome Unit, which was published by American Association of Physics Teachers. Correct use of the radian in mechanics has always been a headache to both students and teachers of physics. The radian seems to make an appearance in places where common sense tells us that it has no business being, and there seems to be no agreed prescription for where it should or should not be used. The EPT Metric Committee attempts here to provide a reasoned basis for dealing with such questions. You can read the rest of the first page of the article yourself. This part basically questions the radian as a unit of angle. Its definition as the ratio of arc length to radius of a circle leaves it as a dimensionless unit. We need some indication when an angle is involved, since not any length ratio is related to angle. The next part emphasizes the relationship between radian and other units of angle. The radian certainly needs to be present if the quantitative measure of an angle is required. You can open the website. Unfortunately, the rest of the article is behind a paywall. Let's go back to previously mentioned problem in current standard, which is inflexibility of conversion between radian and other units of angle in some equations. Normally, conversion from one unit of measurement to another unit can be done before or after the calculation. For example, power equals force times velocity. 1 watt equals 1 newton times 1 meter per second, which is equal to 1 newton meter per second. 1 watt equals 1 newton times 60 meter per minute, which is equal to 60 newton meter per minute. You can convert the unit of velocity first or calculate the power first and then convert its unit later. Power equals torque times angular velocity. In current standard, 1 watt equals 1 newton meter times 1 radian per second, which is equal to 1 newton meter per second. 1 watt equals 1 newton meter times 60 divided by 2 pi rotation per minute, which is equal to 60 newton meter per minute. You must convert the unit of angular velocity first before calculating the power because the unit of angle has disappeared in power. Hopefully, with these limitations of current standard being exposed, we are willing to look for a better new standard. Thanks for watching, and tell me what you think in the comment.